Solving trigonometric equations. Now this lesson takes a little bit of algebra that we learned back in Algebra 2 and the first half of this particular course, and it starts to apply it to trigonometry. In other words, we're going to turn trigonometric expressions, trigonometric unit circle problems into trigonometric equations. Now remember, we are solving equations here, so we still need to remember all the old techniques. We've been solving equations for a while now. For example, we started with solving linear equations all the way back in Algebra 1. This would be an example of a linear binomial. In order to solve a linear binomial, we would just isolate the variable. So we would subtract 1 from both sides, and then divide by 2, and we'd be done. X equals -1/2. We could prove that it's true simply by taking that -1/2 and plugging it back in for the x value. We then could up the ante a little bit. Instead of it being a linear binomial, we can make it a quadratic binomial. Still, as long as it's a binomial, we could still follow the same techniques. Isolate the x variable, subtract 1, divide by 2. But of course, the goal now is to get the x squared undone. And the way we solve any equation, the same way we did it in the linear, the same way we do it in the quadratic. The main goal is to use inverse operations. If you just use inverse operations to get rid of things in reverse order of operations, for instance, we use subtraction to get rid of the addition, we use division to get rid of the multiplication. We're going to do, in order to get rid of a square, we will use a square root. So we'll square root both sides, and then of course on this particular one we'll recognize pretty quickly that, hey, we've got a square root of a negative number, which means imaginary, square root of fraction, which means square root of the top over the square root of the bottom. So square root of 1 is 1, square root of 2 is square root of 2, and anytime you take a square root you have two answers, positive and negative. So while linears were pretty straightforward, quadratics we started to have to remember some extra rules, especially when we threw in a quadratic trinomial. When we do a quadratic trinomial, the technique we would jump to is factoring, and that's what we would basically do for any level of function beyond quadratic trinomials and beyond. We would factor out the function, set each factor equal to 0, and then solve each factor like we would a linear function. So on this one, a trinomial would be factored into a double bubble, in this case 2x plus 1, x plus 1. Set each factor equal to 0, and then solve each factor separately by starting with something complex. For example, the quadratic trinomial, we could then simplify it to something not so complex. For example, the linear binomials 2x plus 1 and x plus 1 that are easily solved. Now in chapter 3 we jumped to a different type of equation. These so far have all been algebraic equations. But then we jump to non-algebraic or transcendental functions, such as the logarithm. But of course, we quickly realized it doesn't matter what type of equation it is. You just follow the same rules. Use inverse operations to get the variable by itself. So on this one, we could subtract 1, divide by 2, just like we normally have. But then we just had to remember the new operation. In order to get rid of a logarithm, we would use an exponential. In this case, a natural logarithm would be the inverse of the exponential e to the x. So we could just e both sides, or exponentiate both sides. X equals e to the -1/2. All right, so that's the old stuff. As we travel into the new stuff, we got to realize it's all the same thing. Solving trig equations. Now, one of the things we need to remember with trig equations is that trig is based on the unit circle. So if you don't have your unit circle handy right now, I want you to go ahead, pause the video, grab your unit circle so that you have something to reference throughout the lesson. And then as soon as you grab that unit circle, I want you to rip it up, throw it away, and I want you to draw a new one completely from memory. Because again, if you don't know the unit circle from memory, this lesson is going to be a waste of your time, because when you get to the assessment and you have to know the unit circle from memory, you're not going to know the unit circle from memory. So take a moment, redraw a brand new unit circle from scratch, and then continue on with the lesson. Alright, so we are solving on the interval 0 to 2 pi. Of course, that tells us two things. First, that tells us that we are officially in radian mode. All our answers need to be in radians, not degrees. If I wanted degrees, I would say solve on the interval 0 to 360 degrees. It also tells us that we only want answers that are on a single interval of the unit circle, from 0 all the way around to 2 pi. Notice I have a bracket on 0, I have a parenthesis on 2 pi. Therefore, I am including 0 as a possible answer, but 2 pi is not a possible answer. If I ever want to answer 2 pi as an answer, I just got to realize that 0 and 2 pi are coterminal to each other. If 2 pi is an answer, then that means 0 was an answer, and I already have 0, so I don't need 2 pi. Now, of course, the unit circle and trigonometric functions, they just go round and round and round and round forever and always. So technically, every single one of these equations is going to have infinite solutions. But I don't want to have to deal with all infinite solutions. It's rare that it comes up that we need to know all infinite solutions. We typically only need to know solutions over a specific interval. Hence why we are restricting ourselves to the interval 0 to 2 pi. Now, other things we need to remember is where within the unit circle trig functions are positive and negative. For example, remember that all trig functions are positive in the first quadrant, sine is positive in the second quadrant, tangent is positive in the third quadrant, and cosine is positive in the fourth quadrant. So on the interval, remember that sine has the same answer in quadrants in 1 and 2. Tangent has the same answers in 1 and 3. Cosine has the same answers in 1 and 4, which means for us, when we're looking for all the answers on the interval 0 to 2 pi, we're going to have 2 quadrants every single time, at least 2 quadrants where we're going to have the same ratio. And thus, when it comes to trig functions, we always expect at least 2 answers. If it's just a regular old boring trig question like this, we are going to expect 2 answers. So let's go ahead and go through the problem just to see what I mean by that. So this one's going to start out just like the linear binomial. We'll subtract 1, divide by 2, and we get sine of x equal to negative 1/2. Now, normally what I would say from this point is to use your inverse operations to get rid of the sine, because that would be the next thing to get rid of. Inverse operation to sine, of course, would be inverse sine. So I could say x is the inverse sine, or the arc sine, of negative 1/2. And based on what you did in the previous chapter, the arc sine of negative 1/2 would be negative pi over 6. But we got a problem with that answer. It doesn't fit in our interval. All right, so negative pi over 6 is not an allowed answer. So what I say concerning inverse trig, if inverse trig is the question, then use inverse trig. But if regular trig is the question, inverse trig can kind of get in our way. What I suggest is let's just go back to the unit circle. Instead of using inverse trig, let's just use the unit circle. In other words, at what angle is the sine equal to negative 1/2? Well, first off, I know that it's negative, so that means I know I'm in the third and or the fourth quadrant. So I want the 2 angles in the third and fourth quadrant that give me negative 1/2 as my sine ratio. So if I either memorize or I look at my recently hand-drawn unit circle, I can see that the y value, in other words, the sine ratio, is negative 1/2 at 7 pi over 6 and 11 pi over 6. I have 2 answers over the interval 0 to 2 pi. Let's try another one. Now notice this one is quadratic. We know what to do when we have quadratics. It's still a quadratic binomial, so we know we're just going to go ahead and solve this one the same way we did the last one, except we're going to go ahead and throw in a square root. So why don't you go ahead and start this one off, give it a try, and start when you get, and replay the video when and if you get stuck. So on this one, we've got our regular old sine function, which we expect to have 2 answers. Now, beyond that, we have a square, and anytime we have a square, we know we're going to have to take a square root, which is going to result in a positive and a negative version of the answer. So what that actually does for us is we can actually anticipate, before we even get started, how many answers we expect to have, which is something you should be doing normally. When we were doing solving polynomial equations a few months ago, I would always say look at the degree of the polynomial to determine how many answers you expect to have. It doesn't work as easy on trig equations as it did on polynomial equations, but you can still predict in advance how many answers you're going to have. Regular old trig questions always have at least 2 answers. If I have a squared trig function, that's going to double the number of answers, because of course a regular trig function is either positive or negative, and it's positive twice, it's negative twice. But if I have a square in there, that means I get to have positives and negatives, which means I'm going to have all 4 quadrants in use, which means I'm going to have 4 answers. So I can make that prediction before I even get started. So now let's just follow the rules. Add 1, divide by 2. Now I can't jump straight to the unit circle here because I'm not done with getting rid of the square. In order to get rid of the square, I'll take the square root. So square root of sine squared is just sine. Square root of 1/2, just like we had before, square root is a positive and a negative. Top square root of the top is 1. Square root of the bottom, can't do anything with that, so that's just square root of 2. Now, from this step, normally I would then look at the unit circle to find 1 over root 2. But of course, 1 over root 2 is not on my unit circle. Anytime I get a number like this that I know is not on the unit circle, I need to do something to it in order to clean it up into something that is on the unit circle. Now, hopefully 1 over root 2 doesn't take you long to recognize that, hey, 1 over root 2 is equivalent to root 2 over 2. In other words, if I just rationalized 1 over root 2, multiply the top by root 2, multiply the bottom by root 2, that simplifies into root 2 over 2. Hopefully you are up to that point with trigonometry that you recognize immediately that 1 over root 2 and root 2 over 2 are the same fraction. So now I just need to know at what angles on the unit circle can I have positive root 2 over 2 or negative root 2 over 2 for my sine ratio. And since it's positive and negative, that means I'm going to use all 4 quadrants. And to get root 2 over 2, it's going to be the pi over 4 intervals. So 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. 4 answers, exactly what I expected. Go ahead and give this one a try. Very similar to the last question. I expect you should be able to do it on your own and then hit play when you're ready. So before I start anything, I want to make a prediction of how many answers I'm going to have. It's a regular old trig function, which means 2, but it's squared, so I'll double my expectation to 4 answers. I expect 4 answers. So step 1, step 2, add 1, divide by 3. Got to get rid of the square, so I'll square root it. Just like before, positive, negative, 1 over root 3 in this case. And just like before, I could rationalize this into root 3 over 3, but remember, every action we have needs to have some reason behind it. It's not just because we can that we do something. It's because it gets me towards something that I can use. Root 3 over 3 is no more useful than 1 over root 3. I'm trying to compare this to the unit circle. I don't see 1 over root 3 on the unit circle, nor would I see root 3 over 3 on the unit circle. I need to remember that for tangent and cotangent, these are ratios. In cotangent's case, this is actually cosine over sine. So when I'm looking at the unit circle, I need to be thinking at looking at not just the x-coordinate and or the y-coordinate, but the x-coordinate and the y-coordinate. And in case of cotangent, it's the x-coordinate divided by the y-coordinate. So then I ask myself, which x-coordinate divided by y-coordinate would result in 1 over root 3? Well, the useful trick that we've used in the past when we have this type of fraction is just to divide top and bottom by 2, and that helps me see the ratios. In other words, the cosine ratio would have to be 1/2. The sine ratio would have to be root 3 over 2, which I happen to know occurs at pi over 3. And since I need positive and negative ratios, that means all 4 quadrants, which is why I have 4 answers. I need all 4 pi over 3 intervals. 1 pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. That's all 4. All right. Notice this one's a little bit different. We don't have a square, but we have what's called a triple angle. In other words, we take cosine of the angle. In this case, the angle is represented by the expression 3x. So this is a triple angle because it's 3 times a normal angle. Instead of it just being x, it's 3x. Now, when we have multi-angles like this, what that's going to do is increase the number of answers that we could possibly have. Now, consider the basic cosine function. If I were to graph the basic cosine function over the interval from 0 to, that would be 2 pi, I get exactly 2 intersections of the x-axis. In other words, over the interval 0 to 2 pi, over the entire unit circle, I have 2 solutions, x equals 0. Now, if I change that to be, say, a triple angle, look what it does to the graph. By doing cosine of 3x, I now have 1, 2, 3, 4, 5, 6 solutions. In other words, I have 3 times as many solutions as I did before. Because remember from graphing techniques, that 3 affects the period. Instead of the period being 2 pi, the period is now 2 pi over 3, which means I can fit 3 of the entire cosine graphs within the interval of 2 pi. We call this frequency. In other words, that 3 affects the period, in other words, the distance it takes before the graph starts to repeat, but it also affects the frequency, which is how often the graph occurs over the interval 0 to 2 pi. Whatever that number is the frequency. So in this case, the frequency would be 3. I get 3 graphs over the basic unit circle interval. All right, so if I change it to, let's say, 5 and made it a quintuple angle, notice I'm going to have exactly 10 solutions. In other words, for multi-angles, you can actually just multiply your expectations by whatever that number happens to be. So if it's a cosine of 10x, that means I'm going to have 20 solutions. Now we got to be a little bit more careful when we're cutting things in half. So like if I, instead of it being a triple angle or a double angle, let's say it was only a half angle. So x divided by 2. So in this case, the frequency would be 1/2. I would have half of a graph over the basic interval. So I only have one solution, which makes sense. I have half the number of answers because I have a half angle. Now, of course, if I divide by 3, there's where we start to get into questions of what does that mean? I have a third of 2 answers. Well, clearly I have one answer. That's not a third of 2. If I were to keep going, let's say I divide it by 5. Let's see if it crosses. So in that case, it actually crossed a little bit short. Let's see if it crossed at 2 pi. Let's see what happened. Oop. Let's go ahead and increase our interval from 2 pi, which is about 6 point. Let's just change it to 6.5. Let's overshoot it a little bit. That way our calculator will see it. So yeah, it looks like it didn't even cross at all over the interval 0 to 2 pi. So when it comes to half angles, third angles, in other words, partial angle problems where you're dividing, it's not as clear what the relationship is. So my suggestion is go ahead for those types of problems, go ahead and assume that you have 2 answers. Assume that you have 2 answers, see what happens, and then if any of your answers are too big to fit in your interval from 0 to 2 pi, just cross out those answers. We'll look at an example in a little bit like that, but you got to be extra careful. All right. We've got 2 cosine of 3x minus 1. I said cosine normally has 2 answers, but it's a triple angle, so I'm going to expect 6 answers. Let's see what happens. So step 1, step 2, add 1, divide by 2. Now, what we're going to do here, we're not going to divide by 3 because we're not ready to divide by 3. We got to get rid of that cosine before we can get rid of the 3. We got to work from the outside in. So to get rid of the cosine, I'm going to go ahead and go to my unit circle at this step. I'm going to ignore the 3 completely. The 3 has nothing to do with my unit circle. I'm going to treat that 3x as if it's not even there, or if it's as if it was a theta. All right, so in other words, at what angle theta is cosine equal to 1/2? Well, I know it's equal to 1/2 at 2 locations. It's equal to 1/2 at pi over 3 and 5 pi over 3. And notice, I didn't write x equals pi over 3 and 5 pi over 3. I wrote 3x because I haven't dealt with the 3 yet. It's still there. It should just come on down. The cosine goes away because I'm going to my unit circle. The 3x comes on down, and that's equal to the 2 angles at which it's equal to 1/2. The cosine is equal to 1/2. But remember, I needed 6 answers. Right now, I only have 2 answers. The way I'm going to get the other 6 is to realize that I can just keep going round and round the unit circle until I have as many answers as I need. In other words, if I start at pi over 3, I know I have another answer exactly 1 unit circle away. In other words, if I just add 2 pi to pi over 3, remember that in terms of a denominator of 3, 2 pi would really be 6 pi over 3. So if I add 6 pi over 3 to 1 pi over 3, I get 7 pi over 3. And I could keep going. I still don't have enough answers, so let's do it again. And basically what I do is I just leapfrog, continuously adding 2 pi until you have the number of answers that you need. So from 5 pi over 3, add another 2 pi. That becomes 11 pi over 3. And then I could keep adding. This time I'll add to the 7 pi over 3. 7 pi over 3 plus 2 pi would give you 13 pi over 3. I now have 5 answers, which means I need one more. So I'll add to the 11 pi over 3, and I'll get 17 pi over 3. Now, of course, you might be thinking this is ridiculous because my original statement or my original direction said I could only go up as high as 2 pi. These two answers are in the interval 0 to 2 pi, but the rest of them are larger than the unit circle. Well, let's realize we're not done. We now have to divide everything by 3. When I divide everything by 3, this 3 finally cancels out. And then all of these fractions, when I divide them by 3, if I divide a fraction by a number, division is in the denominator. So I'm not going to do anything to the numerator. I'm just going to multiply the denominator. Keep it, change it, flip it. If I'm going to keep the fraction, the original fraction pi over 3 the same, instead of division, I'm going to multiply. And instead of 3, it's 1/3. Pi over 3 times 1/3 is 1/9, or pi over 9. So in other words, when you divide the fractions, you're just going to multiply the denominators. So pi over 9, 5 pi over 9, 7 pi over 9, 11 pi over 9, 13 pi over 9, and 17 pi over 9. Now let's look at that largest number one more time and realize 17 pi over 9 is in fact less than 2 pi. Because of course 2 pi is equivalent to 18 pi over 9, and 17 pi over 9 is a little bit shorter than that. So I have all 6 answers simply by exaggerating my answers a step prior. If you didn't know in advance that there were going to be 6 answers, if you didn't do that initially, then you would have had no idea that you were supposed to keep adding 2 pi, in this case 6 times. If you thought there were 4 answers or 2 answers, you would have stopped at that point. You have to know how many answers you're supposed to have in advance before you ever start the problem. Let's try this one. Go ahead and hit play when you're ready. So we are doing a sine function, which means two solutions. It's being squared, so we know to double it into 4 solutions. But then it's also a double angle, which means we're going to double it again. I expect 8 solutions on this one. Let's see what happens. Add 1, divide by 2. We'll go ahead and get rid of the square next by square rooting. We get positive negative 1 over root 2, which we know is equivalent to positive negative root 2 over 2. Positive negative tells me that I'm going to have all 4 quadrants where the sine ratio is root 2 over 2. So that would be pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. But remember, it's a double angle, which means I need to keep going until I have twice as many answers as I normally would have had. So instead of 4 answers, I need 8 answers. So I'll just keep adding 2 pi, starting with pi over 4, then 3 pi over 4, then 5 pi over 4, then 7 pi over 4. So if I add 2 pi with a pi over 4 with a over 4 denominator, that means I'm adding 8 pi over 4. So 1 pi over 4, so 1 plus 8 is 9, 3 plus 8 is 11, 5 plus 8 is 13, 7 plus 8 is 15. You might also notice with the pi over 4s, it's a nice pretty pattern. 1, 3, 5, 7, 9, 11, 13, 15. That only works with pi over 4s, so don't try that with over 6s or over 3s. Now divide everything by 2, and we get all of those answers over 8. Alright, here we have a half angle. So on this one, normally I would expect 2 answers. The half angle, this is where we get a little iffy. I think there's going to be 1 answer. I'm not positive there's going to be 1 answer. Actually, I am positive there's going to be 1 answer, but you don't know that I'm positive there's going to be 1 answer. So let's go ahead and pretend that there's going to be 2 answers, and then we'll just double check our answer at the end. And again, if you're multiplying the angle, go ahead and it's perfectly safe to assume you have a multiple of that number of angles. When you are dividing the angle, go ahead and it's safer just to assume that there's 2, and then double check your answers when you're done. So we'll go ahead and subtract 6, divide by 3. I get secant of x over 2 equals -2. Now this is also one of our first situations where we have one of the reciprocal functions, in this case a secant function. I don't like secant functions. I like sines and cosines. Even when I have tangent or cotangent, I turn it into sines and cosines. So now I need to remember my identities. How do I convert secant into either sines or cosines? And I remember, well, secant is really 1 over cosine. So if I wanted to, I could replace secant of x over 2 with 1 over cosine of x over 2. Notice I didn't change the x over 2. The identity doesn't affect what the angle is. Whatever this is, it's got to be the same angle down here. It's the secant itself that changes to 1 over cosine. Now, I also don't like having cosine in a denominator, so what I'm going to do is I'm just going to go ahead and flip it. Now, of course, if I flip the left side of the fraction, I need to just remember to flip the right side of the fraction. Remember that -2 is really over 1, and if I flip both sides of the equation, cosine moves to the top, -2 moves to the bottom. So we now have cosine equal to -2. Now normally I would say feel free to skip this step. It's not necessary. If you see secant, just immediately replace it with cosine, and then if you're going to replace secant with cosine, that's equivalent to flipping, and thus you have to flip the other side of the fraction as well. That's what I'll do in the future. Now I'm ready to go ahead and go to my unit circle. Cosine is -1/2. Well, cosine is negative in quadrants 2 and 3. Cosine is 1/2 at the pi over 3 intervals. So I want 2 pi over 3 and 4 pi over 3 to represent second and third quadrant. To get rid of the division by 2, I will multiply by 2. So that's going to affect the numerators, which means I get 4 pi over 3 and 8 pi over 3. Now here's where I need to remember, I think there were 2 answers, but I wasn't sure there were 2 answers. Now I can be sure whether or not these answers are correct by realizing I only am allowed to keep answers 2 pi or less. 4 pi over 3 is within that interval, but 8 pi over 3 is larger than 2 pi because, of course, 2 pi is equivalent to 6 pi over 3, and thus that one is not a keeper. We'll just go ahead and ignore it. It's perfectly fine. The answer is not within the interval that we wanted, so we'll just go ahead and ignore it and say we only have one solution, 4 pi over 3. Now the next few examples are going to involve factoring. Sine squared minus sine equals 0. We've got a quadratic right off the bat, so we expect to have 2 answers for the sine and then 4 answers for the sine squared. But then we also have a linear term. Now, of course, remembering back to quadratic polynomials, if we had x squared equals 5 or x squared minus x equals 5, it still represented 2 solutions because it was quadratic. So just because we have a sine squared and a sine, that's not going to double or change the number of answers. All right, simply having a sine squared term means we're going to have 4 answers. Now we have multiple trig functions or multiple functions of various degrees. So if we think back all the way to those first couple slides, when we just had, I think it was 2x squared plus 1. If we just had 2x squared plus 1, we would just isolate the variable. We would use linear techniques in order to isolate the variable. But when we had, I think it was 2x squared plus 3x plus 1, in other words, we had an x squared and an x in there, when you have multiple degrees of the same function, you have to factor. Now in this case we have a binomial, which means the factoring technique that we can use is GCF. Let's look for a common factor. Well, I have a sine squared and a sine. Well, that means I have really a sine times sine and then just a single sine here, which means I have sine as a GCF. I can factor out a sine. And when I factor out sine, that leaves a single sine on this guy minus a sine, take away a sine, that just leaves a 1 behind. So I have sine of x and sine of x minus 1 equal to 0. So we can set each factor equal to 0 just like we normally do when we factor. And now I can solve these two linear type examples separately. We can start with sine of x equal to 0. Thinking about my unit circle, where does sine equal 0? Well, sine equals 0 at 0 and at pi. So I have 2 answers for that guy. And let's see what the 2 answers are for this guy. Well, if I add 1 and then you look at the unit circle, where is sine equal to 1? Well, sine is equal to 1 at pi over 2 and pi over 2. That's it. Sine is equal to 1 only at one location at pi over 2. So you can think of that in the quadratic days, we would think of that as if it was a double root. All right. When sine is equal to 1 or negative 1 or any trig function, if it's equal to 1 or negative 1, it's only going to occur once on the interval. Now I say that, but I'm going to take it away immediately. Tangent and cotangent, those are the special cases. Remember that tangent and cotangent, their period is only 1 pi, not 2 pi. So you'll be able to get still two answers out of those guys. But when it comes to sine, cosine, secant, and cosecant, if it's equal to 1 or negative 1, you're only going to have one solution. So earlier when I said there were 4 answers, what I really mean to say, just like what I really meant to say back in the quadratic days or the polynomial days, at most there will be 4 answers. There will be no more than 4 answers. There's always the possibility of these double root type answers. There's also a possibility of imaginary type answers, in which case in context of this section, we would just simply ignore imaginary solutions and say no solution at all. All right, but this is a limit of possible answers, not always necessarily exactly the number of answers we're going to have. All right, why don't you go ahead and give this one a try. All right. Just like before, we've got sine squared and sine, multiple degrees of the same trig function, so we know we have to factor out. In this case, we'll factor out a sine. So also it's a quadratic, so we expect 4 answers, or at most 4 answers. So when I factor out a sine, I get sine of x and sine of x minus 2, set each factor equal to 0. On the left side, we already know the answers are 0 and pi. On the right side, I get sine of x equal to 2. I look at my unit circle to find out when sine equals 2, and hopefully at this point you have realized sine never equals 2. The largest the sine function ever gets is sine equal to 1. In other words, at 0, it's 0. When I rotate up to pi over 2, it's up to 1, but then as I go further, it starts to decrease from 1. If I think about the trig graph, the sine graph specifically, the range of the sine graph is from -1 to +1. The sine function never gets as high as 2, and therefore there is no solution for that question right there. So I only have 2 solutions, 0 and pi. Remember I said at most 4 answers. This particular one only has 2. Alright, let's look at another quadratic. In this case, we have a quadratic trinomial. So remember, for quadratic trinomials, we need to use the double bubble technique, also known as factoring by decomposition. And the shortcut method, if you recall, is Mr. Scholar's 2 wrongs make a right method. So we're going to start by remembering that it's quadratic, so we have at most 4 answers. And we are going to break this up into a double bubble. The first thing we can do is look at the 2 sine squared. And remember that the beginning of each binomial factor is, instead of it being 2 sine squared, it's just going to be 2 sine and 2 sine. We'll go ahead and ignore the square and just pull down the 2 sine and 2 sine. So that would be my first mistake, because of course if I were to refoil this out, 2 sine times 2 sine is not 2 sine squared but 4 sine squared, but we'll fix it later on. Then to get the other 2 terms, we're going to look at the a value, which is 2, multiply that times the c value, which is -1, and we get 2 times -1 is -2, and we need factors of -2 that add to the b value of -1. So factors that multiply to -2 and add to -1, that would be -2 and +1, and we'll go ahead and put those in place in the binomials. So now that was my second mistake, because of course -2 times +1 does not give you -1 as I would expect it to when I FOIL it out. So then I cover up my mistake by simply simplifying both binomials separately. 2 and 2 can reduce to 1 and 1, so that would just be sine of x minus 1, and the other binomial can't be simplified, so this would be my correct factorization. Feel free to refoil it just to double check. You will get 2 sine squared minus sine minus 1. I've factored it out. Go ahead and set each factor equal to 0 and solve each factor separately. This one equals 1, and of course sine of x only equals 1 at pi over 2. Over here, -1/2, Hey, isn't that the example A we've already answered? Well, that was 7 pi over 6 and 11 pi over 6. Final answer. All right, here's another quadratic trinomial for you to try. This time it's involving secant. Go ahead and pause, try it out, and hit play when you're ready. So secant squared minus 3 secant x plus 2. We'll start by realizing I'm going to have at most 4 answers. We're going to break this into a double bubble. We'll put the secants in first, and then we'll do multiples of AC, 1 times 2, that add to negative 3. That would be negative 2 and negative 1. Sprinkle those in. Nothing to reduce, so that is my factorization. Set each factor equal to 0. We'll go ahead and continue solving the factor on the left. Set it equal to 2. It's a secant. I'm going to change that into cosine, but if I change secant into cosine, then 2 becomes 1/2. Cosine equals 1/2 in the first and fourth quadrant at pi over 3 and 5 pi over 3. Secant equals 1. Well, secant becomes cosine, and when I flip 1 upside down, it's still 1. Cosine equals 1 only at one location, not pi over 2, because that's the sine value. Cosine equals 1 at 0. All right, here's another one, but hey, this one's starting to look a little bit different. The remainder of our examples are going to involve situations where we may have factoring, we may have linear terms, we may have squares, but more specifically, we're going to have multiple trig functions within the same equation. When you have multiple trig functions in the same equation, your first goal needs to be to convert everything to the same equation or the same trig function. I've got sine squared, I've also got cosine squared. I can't have sines and cosines in the same problem, so I need to convert this into something else. Now, this also gets us to the point where there are actually multiple ways we could do this. There are several different options. No one option is necessarily better than the other. So maybe what I do is different from what you do, but as long as you end up with the same answer and everything was legal, then you're correct just like I'm correct. So in this case, we've got sine squared and cosine squared. Now, anytime you see a square, the first thing you need to be thinking about are Pythagorean identities. Remember that sine squared is equal to 1 minus cosine squared. Cosine squared is equal to 1 minus sine squared. So I could replace either of these guys. I could either replace sine squared with 1 minus cosine squared, or I could replace cosine squared with 1 minus sine squared, and that would turn what I have into a different equation that was all the same trig function. It is completely irrelevant which way you go. It doesn't matter. Just pick one. Now, the way I'm going to pick one is I always have a preference. I prefer sine over cosine. So if I have an open option, I'm going to go ahead and replace the cosine with 1 minus sine, or let me rephrase, cosine squared with 1 minus sine squared. Now, I also anticipate having 4 answers because it's still quadratic, because it's got squared terms in it, so I'm going to expect my normal 4 answers. So I have 1 minus sine squared in place of the cosine squared. I've got parentheses and a number outside parentheses, so I know what to do with that because my 4th grade arithmetic teacher taught me to distribute. So 3 minus 3 sine squared. I've got sine squared on both sides of the equation, so I'll just add 3 sine squared to both sides of the equation and get 4 sine squared. Now this problem looks a whole lot prettier, and I can just continue like I did at the top of the lesson. Divide by 4, square root both sides. On the right side, square root of 3 is just root 3, but the square root of 4 is 2. So I really have plus or minus root 3 over 2. And I can pick all 4 locations in the unit circle where sine is root 3 over 2. That would be pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. All right, here's another one, kind of similar to the last one. Go ahead and give it a try. Hit play when you're ready. So I once again have sines and cosines in the same problem, but this time the cosine doesn't have a square, and that's going to tell you pretty much how the only way you're going to be able to do this problem. I can't replace cosine with 1 minus sine because that's not an identity. It has to be cosine squared in order to be an identity. So since the only square is on the sine, the only replacement I can make is for the sine squared. Sine squared gets replaced with 1 minus cosine squared. 2 gets distributed. I now have 2 minus 2 cosine squared equal to 2 plus cosine. I notice I have a 2 on both sides, that positive 2 on both sides, so let's go ahead and get rid of it. That leaves me with negative 2 cosine squared equal to cosine. So now I have multiple levels of the same trig function. Since I have multiple levels of the same trig function, I know that factoring is going to be the technique that I have to use. And if I'm factoring, I got to move everything to the same side, set it equal to 0. Factoring is only useful if it's equal to 0. If it's equal to anything other than 0, factoring is a waste of time. I don't like leading negatives, so I'll just go ahead and divide everything in the equation by a -1, which really just reverses the sign on everything except for the 0 because 0 doesn't have a sign. And now I can realize I can just factor out a cosine just like I did a few examples ago when it was a sine. So I'll factor out a cosine. I'm going to have 4 answers like I said. Cosine equal to 0, 2 cosine plus 1 equal to 0. On the left, cosine equals 0 at pi over 2 and 3 pi over 2. On the right, cosine equals -1/2 at 2 pi over 3 and 4 pi over 3. Here are my 4 answers. Alright, now we're going to start to get a little bit more challenging, but not too much. This time I have secant squared and tangent squared. Give it a try, hit play when you're ready. Now I've got secant squared and tangent squared. Once again, I've got squares, so I should be thinking Pythagorean identities, and if you know your Pythagorean identities very well, then you'll know that secant squared is equivalent to 1 plus tangent squared. Tangent squared is equivalent to secant squared minus 1. Once again, it doesn't matter. I have no preference between these two guys, but I do have a preference for addition over subtraction. Subtraction, you got to be careful about order, so it's going to be much safer to replace the secant versus replacing the tangent. So secant squared is 1 plus tangent squared. We'll go ahead and distribute the 2 like we've done before, and then we can combine like terms. 2 tangent squared plus tangent squared is 3 tangent squared. 2 minus 3 is -1. And now it looks like an easy example from the beginning of the lesson. Add 1, divide by 3, square root, positive -1 over root 3, which is really 1/2 over root 3 over 2. Tangent is really sine over cosine. Sine equals 1/2 at pi over 6, but I want all 4, so 5, 7, and 11 pi over 6. All right. Cosine plus sine tangent. Why don't you give this one a try? See what you can do. Alright, so on this one I don't see any squares, so I can't use any Pythagorean identities. The only identity I really see that might be useful is that tangent. So I can replace tangent with sine over cosine. Now, sine times sine over cosine, that's really just sine squared over cosine. Now I can realize that, hey, I've got cosine plus a fraction. If I want to add these together, I would need a common denominator. For cosine, that's really cosine over 1, and the common denominator will just be cosine itself. So I can just turn that cosine into a cosine squared over cosine. Now I have a common denominator, so I can add them together. I get cosine squared plus sine squared. And I should hopefully realize cosine squared plus sine squared, that's just 1. That's a Pythagorean identity. That's our original Pythagorean identity. Cosine squared plus sine squared equals 1. So I'll just replace it with 1. So I now have 1 over cosine equal to 2. I just took something that looked kind of complex and made it into something that's really quite simple. So I now have 1 over cosine. Now if I want to flip that upside down, I can just do the same thing to the other side and get cosine equal to 1/2, which has 2 answers at pi over 3 and 5 pi over 3. Alright, so this one will be our final example, secant plus tangent. It looks pretty simple, and it's simply how it works out. The ones that look uglier are usually pretty easy, and the ones that look pretty easy are usually pretty deceptive and are actually a little bit more challenging. So on this one, I don't see any squares, so the Pythagorean identities are off the table for now. The only thing I could really do is convert to sine and cosine, so that's what I'll do. Secant is 1 over cosine, tangent is sine over cosine, which means I have a common denominator and I can add them together. 1 plus sine over cosine equal to 1. I can now get rid of the fraction by multiplying both sides by cosine and get 1 plus sine equal to cosine. And here's where I kind of really have no idea where else to proceed. I've already converted everything to sines and cosines. I can't use any identities. There's really not much option except for one option that really kind of rarely comes up. And that's just to square both sides of the equation. As long as you do it to both sides, it's perfectly legal. And by doing that, it's going to allow some Pythagorean identities to come into play. On the right, I have cosine squared. On the left, if you're still saying 1 plus sine squared, I need you to stop this video and go back and relearn Algebra 1. 1 plus sine, quantity squared, is really 1 plus sine times 1 plus sine. And when I FOIL out 1 plus sine times 1 plus sine, I should get 1 plus 2 sine plus sine squared. Now that I have some squares, I can use a Pythagorean identity. Cosine squared can be replaced with 1 minus sine squared. I can then combine like terms. The 1 is going to cancel out. The negative sine squared moves over to the left side as 2 sine squared. Everything's got a 2 in front of it, so I can just divide everything by 2. It's also quadratic, so I know I'm going to have 4 answers. At most 4 answers. Again, I divided everything by 2. I can factor out a sine because it's a quadratic binomial. That leaves me with sine and 1 plus sine. Sine equal to 0, 1 plus sine equal to 0. Sine equals 0 at 0 and pi. 1 plus sine gives me negative 1. Sine equals negative 1 at 3 pi over 2. And you may think that we're done, but we're not. I said this one was challenging, not so much because of that squaring technique that we needed back then, but it's extra challenging because this one actually only has 2 solutions. Think about that 3 pi over 2. Let's go back to the beginning. Secant and tangent. If you think back to when we were graphing the secant function and the tangent function, secant and tangent both had asymptotes. They both had asymptotes at the same location. Those asymptotes were at the first and the third tick mark. In other words, pi over 2 and 3 pi over 2. 3 pi over 2 was one of the asymptote locations for secant and tangent, which means secant and tangent cannot have solutions at 3 pi over 2. So where did that 3 pi over 2 come from? It came from what I have circled here when I squared it. When you square a function, if you take a linear function which has one solution and square it arbitrarily, you're now taking something that has one solution and turning it into 2 solutions. You are doubling the number of possible solutions. When you square the function, you are increasing the degree and thus increasing the number of answers. But remember, that was not the original question. The original question was secant tangent, so you have to go back to the original to check for extraneous solutions. Anytime you change the degree of the problem, just like we did with absolute value equations back in Algebra 2, just like we did with square root equations in Algebra 2, just like we did with quadratics when we used this technique earlier in this year, when you change the degree of the problem, you have to check for extraneous solutions. So 3 pi over 2 doesn't fit into the secant plus tangent. My original function should have only had 2 answers because it was just a linear type problem. There was no squaring going on or involved. I changed it from 2 answers to 4 answers, which means any of those extra answers that it came up have to be ignored. There is only 2 answers, 0 and pi.